Знову так.
Так, щоб сторінки було видно.
Угу. Так.
Ми маємо почати вчасно, зараз лише запускається трансляція, тому о 4 ми зможемо розпочати. Ми все майже готові.
Домовились. Тоді чекаємо ще кілька хвилин. All right, I guess we can start now. Hello, this is a third lecture on audio processing, and today's topic is modern text-to-speech models. So to start, let's describe what kind of problem we are aiming to solve. Suppose that we have a sequence of letters, like some phrase, and a corresponding audio file to this text is our pair of text and audio, and we have a data set of these pairs. And we want to design a model which is able to take only text as input and synthesize audio. And the goal of this model in the end is being able to synthesize arbitrary text sequences such that model is generalized and is able to speak no matter what kind of text it provided. It have seen it on training, like this particular sequence of the words, or haven't seen it, it should be able to pronounce it clearly. And better in some pleasant sound, which we humans find non-robotic and interesting to listen to. So the first interesting models, in my opinion, started to appear in around 2017, 2016, and the biggest contribution to this field was brought by the Google's Tegatron speech team. I'm opening their website with the list of their papers. All of those are available on the archive. So you can see that the first Decathlon paper, it appeared in the March 2017, and they are pretty productive. So they have a lot of interesting papers, and they still actively research this topic. So you can imagine that this field is really big. And I encourage you to explore their list of the papers. Some of them are crucial, like a first Decathlon paper and the next version of the Decathlon, Decathlon 2, which is named here the natural TTS synthesis. There is many research on the prosody, on the transfer of the emotions, how we can effectively represent these data in our models. So that is really cool. So many of ideas from here are great, and it is interesting to develop based on those ideas, trying to find how we can go even further from these ideas. One more a group which is doing also many contributions to speech synthesis comes from the Baidu research. So they have also quite a list of the publications, and they also have good models for ASR. So they have mainly two types of models: the deep voice, which is text to speech, and deep speech, which is speech to text. And you can find all of these publications here. Many of those papers have been implemented by some researchers, and they are available on the GitHub. So explore them. Same goes to the Decathlon. Usually, Decathlon team and Baidu teams, they don't publish their code for their papers. I guess the reasons are obvious. They might want to commercialize their research and don't want to reveal some secrets, which is perfectly legit when it comes to some research, not in academia, but in industry. One of the drawbacks of Decathlon and Baidu papers, when you read them, you can clearly get an idea of the model they're describing, but in many cases they use some in-house data sets which you don't have access to, and that is the big problem of reproducibility of their results. So usually it's hard to reproduce these values, and you should just only read carefully the papers, try and be thinking logically and what they are doing there, and you can only trust their results and try to check them on your experiments. Okay, so these two groups, I guess, the biggest ones, which do the publications of their research. Okay, so we can treat a TTS model as just a function which is doing the mapping from the text, these like sequence of the characters, to the sequence of the spectrogram frames, starting like from 1 until ST, where T stands for time. Also, it worth to mention then that number of the characters for sure is not the same as the number of the time frames. So, and usually n is less than t. And these this also brings like some complexities inside the model. You just cannot like look at the single character and produce the mapping of the single frame which corresponds to the single character. In many cases, you should look to like the multiple characters and create like a new frame. So it requires to have an alignment between the sequence of the characters and the sequence of the frames. Also, one interesting observation, we can think about text as the like some compression, some compressed code of corresponding speech. So just imagine that like a single word have been pronounced by many people, like, for example, the population of this planet, like it was pronounced 7.5 billion times. And everybody of us has our own voice characteristics, our own like ways to express emotions. So you can imagine how diverse are the resulting sounds. But the graphical representation of this single word is just like 5 letters, and that's it. So that is like their biggest issue of the TTS. We basically, by doing TTS, we are designing a kind of a decompression algorithm, which takes there as input the sequence of the letters, this compressed code, and its task is to decompress it to a variety of the ways of how people speak. So let's think about like why text-to-speech is hard, like other aspects. It's very like luckily that English and other European languages, they don't have like difference of the meaning of the words, which is based on just the tone of the vowels, which is not the same for some Asian languages like Chinese. And there, the meaning of the word can be like completely changed depending on the tone of the vowel letters. So it also can look like a graphically very similar representations, but the like resulting speech is can just change the meaning of the sentence. So we also have these problems, for example, in English. Let's consider like the word read. Like read in the present is just pronounced as a read, here is the transcript of this word. And in the past, it's read. So they are written the same, but pronounced differently. And this difference in pronunciation is dictated by the context. So there is no way to understand how you should pronounce this word when it's just isolated and taken out of the context. And these kind of mismatches, they are like everywhere in languages. In Ukrainian as well, so we have many of these problems. And this misalignment, it makes the task of the speech synthesis models even harder, since to pronounce these words correctly, they need to keep the context, what they have seen like previously, and based on what they've seen previously, they need to adjust what they should pronounce in this particular time. So it also means that by its nature, the synthesis of the speech is sequential. So it might be possible to synthesize speech like in parallel, but we need the context from the past. That is like the nature of this task. Also, there is like an interesting aspect to speech. We can think about a speech signal as a linguistical content. So that is like the meaning we want to deliver. We can also think about it as it was said by somebody, like who is the source of this speech. And like third component, it can be like a prosody. And prosody means all the unexplained, crucial things which we are like, which is hard to classify for us. And the prosody is about intonation, the intention. So we can express emotions by the means of the prosody. So prosody encodes all of these hard to classify information. And basically prosody, that is the thing which makes synthesis natural, non-robotic, and interesting to listen to. And regarding prosody, it's a very like early days study or even science of the prosody. There is not that many papers on prosody. There is like many conventions what we can understand under the prosody. So, but all people agree that prosody conveys emotions. And when we want our model to sound natural, we care about prosody. Okay, here is the picture of the basic decatron architecture. And we'll stop on this slide and I'll describe in more details what's going on here. So as I said before, we have text as input. And this part, the model, just can be grouped and named collectively as some encoder. So it basically means that we take as input some text and we want to process it in the way such that it will be enriched and will have some useful contextual information which is helpful for the synthesis task. This part can be just named as the decoder. So what it does, we have like encoded text, we have this module of the attention, which we'll cover. And then our task is to produce the actual frames of the spectrogram. Given the text we've processed. But to achieve this task, we also need some meaning of alignment of the text with the MEL spectrogram. So we need this attention module, which is like the purpose of it is to build an alignment. And it turns out that this task of aligning the text sequence with the audio sequence is really hard, since, in my opinion, building alignment itself is very important, and it's also a very hard task, since Decatron can even produce really well-detailed spectrograms, even without looking into the text. That is not what we want to have. We want to have a model which looks into the letters and produce corresponding spectrograms. And the reason why decoder is able to produce crispy, nice-looking spectrograms, even without looking into letters, is because it has a mechanism of cheating, which is the teacher forcing. We'll cover this mechanism as well. So the model is learned using the, let's say we are in the space of the pictures. The MEL spectrograms are valid images, so we can use some mean square error. So that is like an L2 distance between the spectrogram, the predicted spectrogram, and some target spectrogram. We computed this loss, it's a scalar value, and we are starting to, let's start from here. We don't have WaveNet so far, so that is a bit like, not from this diagram. So we are starting to backpropagate our signal And with the gradients, which convey useful information, we are learning all of the layers of the decoder, of the tension layer, and up to text embeddings. So you can imagine the complexity of this model, and that the gradients should travel really long way to update the weights of the first layers of the character embeddings. So this supervision signal can get weak over a backpropagation process. And we don't want it to be weak. We want it to be useful, and we want our weights being updated such that the synthesis will get better. Also, here is one important component, is like a prediction of a stop token, since it can also be treated like some hug. It's not very crucial, but it's important for this model being functional. So this component is necessary for model just to stop talking, and it's just like a softmax output, which tells we know the target length of the MEL spectrogram, and we do the synthesis, and during training we have targets when the model should stop, and we have a hope that when it learned where to stop on inference time, we'll have a probability if we need to continue synthesis, or we can just stop now. I guess I need to remove those annotations. Clear. Okay. So let's start looking into this architecture step by step from the encoder. As I said before, we need the context being encoded into the letters. By the context, we can mean some n-gram representations. What is n-gram? In case we have some letter, we have some neighbors to the left, neighbors to the right, and with the simple convolution of the kernel of the size of the 3, we can get some n-gram, 3-gram representation of this letter. That is an intuition what the convolution layers can do with the letters. And we need these n-gram representations to be more rich, to have more meaning from the past, and even maybe from the future as well. It is purely valid to hold information about the past and the future for the text information. But it's not possible to have this information about the future from the past in the decoder. Because when the decoder will have information about future, given the task, it is forced to predict a single frame in the future, it can start cheating. And it will not learn something useful. It will be just copying information from future and will not learn something useful. So getting back to the encoder. We can represent letters as some one-hot encodings. So given like the English alphabet, we can have like a vector of, for example, can be, let's say we have some 40 characters. It's like letters plus punctuations. And that is, it's not even real, it's natural numbers, but doesn't matter. And we have this one code encoding for every letter we have in our text. And then we would like to get from these one code encodings using embedding layers to high-dimensional representations. So we have an embedding layer here, embedder, which outputs vectors of some like higher dimensionality. It can be like arbitrary pi, but let's say be 256. So that is not real, but let me clarify myself. So that is like natural numbers. But it's, I don't remember exactly, but you got what I mean. So we have an embedder which outputs these big dimensionality vectors for every letter. And then we have like a stack of some con layers, which is here. And in this way, we collect the contextual context builder, let's say. It's a purpose of the context builder. So this stack of the layers will give us as output some n-grams. N-grams. And then we want to even more like smooth the representations of these letters, and we run the bidirectional LSTMs such that the outputs of these like text encoder will be the effect of reading force and back. That is what the bidirectional LSTM will do for us. So it basically means that the last characters of this sentence, experiments and 3 periods, will hold some information even about the beginning of the sentence. And this amount of information will be gradually like less and less and less and less present towards the end. Same holds for like the beginning of the sentence. So we will get some information about the words which are coming after, right in the beginning, which basically makes sense because when we are reading, we are looking at some like portion of the text. We have like our attention concentrated on some part of the text, maybe one sentence, maybe like several sentences, but we don't like look at all the like pages of the book at once. So, and this information about how we'll finish the sentence can affect the way we pronounce the words in the middle of the sentence. That is like the importance of having this bidirectional smoothings. That is like my interpretation why we need them. Okay. We've covered the part of the encoder, and so as a result, we have some feature map like this block. It's an output of the encoder, which like lives in some space, which is like the number of the letters. Let's name it C, number of the characters, and the dimensionality of like the hidden number of the hidden units for every letter. Let it stay the same, like 256. So here we basically have like the embeddings for every letter goes like this. So that's what we will give as information to the decoder. That's what it will see. All right, so as I said before, we can treat decoder as an autoregressive module, which takes those features as supplied by the encoder, and its task is to predict autoregressively one frame at a time of the spectrogram. So to start the prediction, we have some like placeholder value, which is like a start of a sequence. Because it's an autoregressive module, we can model this process as some like a recurrent model running forward. And this recurrent model, it takes as input the like some contextual letters and the previous prediction on inference time. On the like training time, we are using the teacher forcing. And the purpose of teacher forcing is like, there is like many, on one hand, I treat it like as one hack in decoder, and it makes like it brings one more layer of unaligned tasks on the training and inference, since on training we force the target frame. So imagine we have these. Oh, I have a slide for teacher forcing. Maybe I'm telling more about. No, it will be even better to show it here. So this is like a target spectrogram. This one is a target. Here we are doing a prediction of the first column of the spectrogram, like one frame at a time. So that will be like frame ST. We are staying at 0 right now. So our like recurrent based model, which is here, it can take the previous frame as input target previous frame. Some weighted context information as a text, which is dictated by attention. These are like two inputs. And it outputs every time new prediction of the frame. And it goes like this until the end of the target frame. So far, so good. But on the inference time, we don't have this spectrogram. We don't have target, right? We want to synthesize. And the best we can do in this scenario, we are forced not to take from here. This is like training path. But we are forced to take from our predictions, our own past predictions, to do the inference of the next frames. That is, you see this misalignment? We are doing one task on the training, but we are doing completely different job on the inference. And that is not like very good. And there are like many papers who are trying to bridge the gap between the inference procedure and training procedure. And there are like some GAN-based algorithms which are trying to simplify the process of teacher forcing, which are like trying to distinguish which spectrogram produced with the teacher forcing, which is without teacher forcing, and we want to those produced without teacher forcing being similar to the real ones. So there's many approaches which are trying to overcome this problem. But in this scenario, in particular, this model, teacher forcing is necessary for one purpose. We want our predictions and targets being aligned. So imagine that we have the same, we have a model which is doing its job like perfectly. It's predicting very well all the frames. But imagine that we have this target, but it's shifted in time. By like, even like several frames. So it's like it's shifted by 2 frames. 2 frames. And then when we start computing the mean square error loss, first of all, we are screwed. Predicted everything well, but since it is not aligned, the loss will be huge, and model will not learn something useful. So we want to enforce this process of like alignment, the predictions and the target. And in my opinion, that is one of the most important roles of the teacher forcing, to enforce this relation between the predictions and the targets. And teacher forcing, that's what makes training possible in Techtron-like models. There are like new approaches, as I mentioned on the previous lection, like very recent from the DeepMind, there is a paper when they don't use teacher forcing, which sounds really great to me. It's like a breakthrough. But they use an idea of the dynamic time warping and some hacks in how they align the sequences of the text with the sequences of the spectrograms, and a lot of GANs well, I haven't studied this paper good enough to explain you now. But I guess that the crucial part here is to use the dynamical time warping, which makes, in case we have target, which is like 400 frames, and we have some prediction, which is some different amount, like 420 frames. Then we run these like target and predictions through DTW, and we can align the prediction with target using this alignment procedure. And that way, the model is trying to learn to like minimize the distance of the predictions from the targets. It's penalized by being not exactly the same amount of the frames, and it tries to do the good job. So that is, I guess, an interesting way of the evolving of these algorithms. But it was to take a closer look at them. Okay, so the first purpose is of the teacher forcing is to get an alignment. Second purpose is to make training feasible in Decathlon scenario. As I told before, like the problem of alignment of the text frames and the spectrogram frames is really hard. And this kind of attention between letters and spectrogram frames for the well-learned model, it looks like this. What we can see here is that, let's start reading this plot. So on the horizontal axis, we have spectrogram frames. On the vertical, it's letter indexes. And this is like the same phrase I've used before. It has used, other, treasury, and like this. So it starts here, and it tells that in order to produce first, I guess, around seven frames of this spectrogram, the model needs to look only at the first letter, I. That might be wrong, that might be right. But basically it means that we are looking into the letters, and in a monotonic way, we are just moving by the text, and we are reading it. So we can also study these like alignments and take a closer look at some like long places. These might correspond to some pauses. These like maybe pause here as well, like some token which, sorry, not token, but some letter which lasts for a long time. So that is like rich information which is necessary for a decoder to basically pronounce something. It needs to know for how long every letter should be like pronounced. And like most of the attention-based models, they can be simplified to simple dot product attention. we have some memory. By memory, I mean encodings of the letters. And we have some query, like at some point in time, let's say we are synthesizing let's say we are synthesizing something here. And that is like a corresponding synthesized spectrogram to this alignment. So during the process of the synthesis, we have a query, which can be like an embedding of the like the previous frame which we have. So that is the query. One letter is enough. We also have our memory, and our memory is just our features which are coming from the encoder. Memory comes from encoder, and it is like number of the letters, characters multiplied by 256. So then we can take this query and compute the dot product with every, and this query is in the space of the 256. We want to do the valid dot product. So we are taking each cell from the memory. We are taking the query, and we are computing the dot product. Then we just write down the responses, which is the like lives in the space of like reals and number of the characters, and we do this softmax. That is the way how we can. So we apply some softmax fun. So let's name it like some responses. And then we take a softmax of these responses. And that is like the answer on the weights for every individual character, which is necessary to synthesize the next frame. And then when we have these responses, we can do like find the linear combination of our memory cells, which basically shows us how we should combine the available letters which we have from the encoder in order to synthesize only this frame. This like style of attention, it doesn't have the property of monotonicity. We can add this as well, but it's like a basic way how attention works. We are trying to find the correlations of the appropriate letters which are necessary for us to speak this word. And regarding the monotonicity and non-monotonicity, Why do we need monotonicity? Because we want to have an experience of the reading, right? We don't want for our model to jump from one place to another place in order to say like this word correctly. We just implicitly constrained it to just go monotonically from the start until the end of the text. And that is like the example to the right of the monotonic attention. We can just like while we are computing this monotonic attention, we computed the attention like the first time, we've memorized the place where we like was the maximum amount of the energy for the context. Then we just start from this place and go force and force and force and force. So we just trying to accumulate like the context where we stopped before. And this way we are just making the space of their lookup for the relevant letters more like narrow. And it's necessary for us just to keep going forward. To the left, there is a picture of non-monotonic attention, and it is roughly like what happens with the attention mechanism I've described schematically. You do not have like any constraints on where you've been looking to the letters before. You are free just to pick like any cell you want to from the memory. And this is not desired behavior in text-to-speech, but it might be absolutely fine for some tasks of image annotations, like image captioning. For example, you can imagine like some picture, there are like some objects in there, and you just write in the sentence about this picture, there is a house and the dog is running, and there is like clouds here and the tree, which is to the right. So for this purpose, model might benefit from moving like from one spatial location to like some other place. So there are applications for this attention I've described. In case you're interested in how to implement like monotonic attentions, there is a great paper on this, on the enforcing of the monotonicity of hard alignments. And there are like many approaches to how we can compute the attentions. Also, I wanted to tell like a bit about the very popular transformers right now, and why I don't like them for TTS purposes. For example, it's not clear which head of attention in transformers holds this alignment. And in the papers I've seen, it turns out that one of the heads is basically learning this monotonic alignment, but you don't have like control on it. Like some like random head can be picked in your model, and it will learn this monotonic behavior and how to read the text. Since it turns out that it's necessary for the model being able to synthesize what it asked to synthesize. some technical problems, and I finally rejoined. Hopefully you can hear me well.
Ross, yes, we hear you well.
Great. So let me screen share. Okay, so regarding the attentions in like transformers, these multi-head approaches, it turns out that one of those learns this monotonic alignment, but some other heads may learn something useful as well, which might be useful, might be not useful. We don't really know what they learn. I guess it's impossible to give some interpretations here. Maybe it's like some prosodic information, who knows, maybe like some grammar like informations that like saying what word we are pronouncing now is related somehow to some words in the future, but some particular words in the future and some in the past. So it's really hard to deal with it. These kind of alignments where you have like a single alignment between the decoder and the encoder, they are much easier to debug. You can have like a clear picture of what is happening inside your model. So that is my view on this. There are like alternatives, which I said in the recent DeepMind paper. They are not using the idea of attention at all. They are like using some ideas of like this dynamic time warping and some other ways on how to align the sequences. So that is, I guess, an interesting topic for the research on how to align the sequence of the letters with the sequence of the speech frames. But now, yeah, regarding attention, I guess it's the most fragile part in the TTS pipeline. It's really easy to break it. You can have, like, as I said, a decoder which is doing its job well because it has teacher forcing and can even not take a look at the letters. And the attention will be broken and you just have like some random values in there. It is not easy to have this attention like visible, which is monotonous like here when you just start training from scratch. This like even when you just clone the Tekkatron code available on the GitHub, like public implementations, and you just start training from scratch, it takes a lot of the time for attention to appear. It starts from like very smooth or maybe even random values, and it sharpens gradually to the convergence time. So it's interesting to look at how your model evolves during the training process. And alignment learns very like not very fast. You need to spend time to learn it. And it can be not exact, can be misleading. So when you have it, you can debug and take a look where your model actually looked for when it synthesized like some particular words. And it can give you some insights on what might be broken in your model, where you can take like more closer look to fix problems. So that is good information for debug purposes. Yeah, I told this that the attention is just set of the correlations between the query spectrogram and the memory bank. So we just store how the frames in the speech are correlated with the letters. And the purpose of the attention, we want this module to guide the process of the synthesis. And that's why we want it to be monotonic. We don't want to speak like the word from the end of the sentence, then just get back to the beginning. We want to go it smoothly from the beginning until the end of the sentence. And this should be a guide of the synthesis process. And let me show you some samples of the synthesized audio. It's nothing like it's just an open source implementation of Decatron from NVIDIA, as well as their implementation of the vocoder, which basically takes those spectrograms and turns them into the waveforms we can listen to. So here we have this text. It has used other Treasury law enforcement agents on special experiments. That's a picture of the alignment. That's the picture of the synthesized spectrogram, basically an output of the Decatron model. And that is what we get from the vocoder. I've pre-processed all of these inputs, so I synthesized this phrase in Decatron and then created a waveform via the open source Waveflow implementation. So please listen to this audio sample.
It has used other Treasury law enforcement agents on special experiments.
So it corresponds to the text we supplied, but you might notice that in the beginning there was like some trembling in the voice, particularly when it said like it has used. It was not very natural to me, but all the rest words was like sounded okay. We will not touch vocoders here during these lectures, but I will show like a brief introduction into vocoders and what we can do even without like training vocoders. Because as I said before, to get a waveform representation, we need magnitude and phase. And what we get from the Decatron is only magnitudes. We don't have information about the phase. So basically, we can treat vocoders, which we use now, are like some machines which take these 2D representations of the spectrograms from Decatron or other models and turn them into waveforms, trying to reconstruct the information about the phase. Okay. So a bit more words about teacher forcing. Yes, so teacher forcing is a technique which uses ground truth spectrogram for predicting next frames. In this way, we make the task of the decoder much easier. So it can not look into the text at all and makes training possible since it imposes the alignment of the predictions and targets. And also one important note is that in case, even if we'll know, like we know this, right? We know the length of the spectrogram, like the target, it's like 400 frames. And we do not force do not do like the teacher forcing. We don't give as inputs the real frames from the past, but we only do like force the like predictions. We can easily get the same number of frames by just stopping predictions at 400. That's it. So we will have like the same amount of the frames, but we still, in this way, even when the number of the frames will be the same, there is no guarantee that the alignment is there between the target and the prediction. So there are like other approaches which can be done. We can go for some perceptual comparisons. For example, not using this L2, which is fragile. When you just shift by 1 pixel, you are screwed. So we can try do some even some ASRs, like whatever tells us if the words are like there in prediction or target. We can experiment on this. But for now, what is feasible is to do this teacher forcing trick and stay in the space of the L2 comparisons. But there is like many ways on where these can be evolved, and we can get like better models in case we'll not be attached to the spatial positions of the individual frames. So that is also an open question, how to design a better loss function for text-to-speech models. And as I said before, on training time, we have a decoder. It's like a function which takes a previous frame, the real frame, and some context information at time t. So frame from the past and necessary like weighted letters for the current frame, and which outputs the next, current frame. And during the inference time, what is changing, we are feeding in the own prediction of the model. And that's what we are like doomed to do here, since we don't have like any ground truth. That's why, that is like the reason why teacher forcing is not ideal, since these two scenarios on training and inference, they are like not aligned, and that is like makes process more complicated. Also, in case we feed in like the predictions, will during the training, the way we do in the inference, will accumulate the errors from the past, and the model will just get lost. So it is interesting to experiment on this. There are like many thoughts how this can be improved. And yeah, this component is a bit questionable if it's like really needed to work so. All right, I promised to take like quick look at the phase reconstruction or the like vocoders, very basic vocoders. And here's the one of those. Its name is the Griffin limb. It's very simple, and it is widely used during the like debug process of training your text-to-speech models. Maybe you don't want to wait for like full synthesis of the waveforms by heavy-weighted vocoders like WaveNets, WaveGlows, and etc. Maybe you want to just have a glimpse at how the outputs sound, and that is like the way to achieve this. So what I'm doing here, I'm using the same waveform. Yes, which we've listened to before. And this one synthesized sample of the speech. I am extracting a short-term Fourier transform spectrogram. Here I'm building the layer itself. This is also in the code I've shared yesterday. Then I'm applying the transform this WAV file. So this transform returns me the magnitudes and phases of the spectrogram. Then I plot the magnitude spectrogram, which is here. And also I plot the phase spectrogram, which looks random. And that is one of the reasons why we don't usually use phases in training neural nets, at least in the representation of the like spectrums of the phases, because they look random. And convolutional nets, they are like everywhere there are correlations, and they're designed to look for correlations. So there is a hard chance to find any patterns which are repeating. So that's why we are just operating on these images, on magnitude spectrograms. Okay, so the picture of the magnitude, of the phase, and then I apply a Griffin-Lim algorithm, which takes as input only magnitudes, and it initializes phases randomly and goes through the procedure, like iterative procedure of making the inverse Fourier transform with the same magnitude, but the like randomly initialized phases. We are doing inverse STFT. We are getting back into this space of the in the time space. Then we are making again STFT. We are getting into the space of the spectrograms. We are not changing the magnitudes. We are just updating the phases. So iteratively, we are trying to get better phase. And that's what the documentation of the Griffin-Lim says. So given a short-time Fourier transform, the magnitude, that's what we have. The algorithm randomly initializes phase estimates and then alternates forward and inverse STFT operations. So the algorithm itself is there is no example of it in implementation, but it is like about 5 rows of the code. It's very simple, and it gives results which sound fine. Oh, here are given some patterns in this, but again, these patterns doesn't look like they can be somehow used by neural nets. At least I was not able to get something useful of the phases represented this way. And let's listen to the result of the this process of the reconstruction. So let me reiterate. As input, we only provided this MEL spectrogram, and as output, we we created something which sounds like this.
It has used other Treasury law enforcement agents on special experiments.
So you might notice, let me play again the synthesized.
It has used other Treasury law enforcement agents on special experiments.
It sounds to me that like the approximated version by Griffin Lin, it sounds a bit more robotic.
It has used other Treasury law enforcement agents on special experiments.
So it's not like definitely an algorithm which you want to use in like some production or purposes. But just to have like a short glimpse on how your spectrograms sound, it is fine, it is fantastic. So that is like the only work order which we are covering here. Since it's like also a big topic, and I want to focus us on the parts of the prosody and what we can do with the text-to-speech. It means that in case we have like a perfectly created spectrogram, then the process of getting to the waveform is much easier, in my opinion. So good looking spectrograms first, that is my goal. Okay, now let's talk about how we can extend text-to-speech models. First of all, there is a great thing as phonemes. Phonemes are units of the speech, and they provide us more exact mapping of the sounds to their like graphical representations. I guess that everybody has seen phonemes in some textbooks of learning languages. They help learners how to pronounce correctly words, and since sometimes you just don't know the rules of the pronunciation, and phonemes can help. But for this reason, you need to learn how to read phonemes. And in my opinion, there is not too many people who really understand how to read phonemes. I cannot read them well as well. So I know how to read some of them, but phonemes is like something better understandable by the phonetics researchers. But anyway, phonemes are helpful in meaning that they just provide us more exact mapping between graphical representations and sounds. There is like a set of the phonemes which is defined in the International Phonetic Alphabet. They are divided by the consonants and vowel sounds, and this is like the whole set of all the available phonemes. We can also have some like information about the longevity of some sounds, some stresses, and like many more features which show how the phonemes should be pronounced, as well as for tonal languages. We have like the like 5 types of the tones available for some sounds. So they're like more high-pitched, low-pitched, and as I said before, in some languages, the proper tone dictates the meaning of the word. So for English, it's not very relevant, but for some Asian languages, it is very crucial to speak phones correctly, and hence synthesize phonemes correctly. And let's take a look why we might want to use phonemes. So, like, one of the observations is that attention in space of letters is ill-defined. Let's consider like one word better. It has double T. And now there is the question, how we should align these two T's to speech frames. In case the duration of T is like some arbitrary like 5 frames, should we have like 2 frames of first T and 3 frames of the second T? Or should we have like 0 of the first and 5 of the second? That's like ill-defined. In space of the letters, it's not clear how the alignment should behave. And this adds like a complication to the model. In case we are getting into the space of the phonemes, we have like a singular representation of this double T, sound phone, which should sound like T, but I don't know how to read it properly. So again, phonemes can be helpful to make the problem of alignments between the text and speech frames more like better defined. But also like phonemes, I'm referring to phonemes which we can get using the eSpeak library, as well as like Phonemize is a great Python package which has many backends, eSpeak and others, but it allows you just to take some text like here and get a phoneme transcript of it. So that is same text we had before, like phoneme, sorry, some other text. I'm just making out this text to show where phonemes are cool. So phonemes are cool, and we see that the correspondence to double O here is just U. And it says it's a long U, okay. And coordination. And here we also have like graphically like double O, but the reading of those two O's is different. So it's one O and something phonetically unknown to me, but it's definitely a different representation from just a U sound. Of a model is much better, this example with the better we already seen. And also we are hiding some unvoiced letters like H here. You see that it corresponds to 3 phonemes. And here as well. So like it makes the representation of the sounds more universal across the languages. Also, it's great that the next generation of eSpeak, eSpeak NG, it has our support for like 120 languages and for Ukrainian as well. And this sentence says in Ukrainian, фонеми – це елегантний спосіб кодувати текст незалежно від мови. So it means that the phonemes are like an elegant way for encoding text, language independent. And we have this phonetical representation of the Ukrainian text, which can also be pronounced by some speakers who haven't seen Ukrainian at all. And that is a great way to build some multilingual text-to-speech models. And I guess that phonemes have a big future for text-to-speech synthesis. But there are like some problems right now with phonemes. First of all, the conversion from the phoneme, from text to phonemes, it's based on some predefined dictionaries, and these dictionaries, they just don't handle all of the possible cases. So these phonetical transcripts, they are far from being exact. But also, there are like some research topics on the neural grapheme to phoneme converters, and grapheme is just a cool way of saying letters. So we have a model which takes as input like some sequence of the letters, and its task is to produce phonemes as output. So they might be like more robust, but even given those freely available tools like eSpeak Next Generation and the Phonemize great library in Python, we can do these manipulations, and that is exciting. Yeah, and basically we can this way train some multilingual text-to-speech. Regarding the supported languages, there are like many of those. I just listed like some 10 random languages. The most of those I have even heard before, like Sinhala and these kind of stuff. But it's great to explore it and use it in speech synthesis. Also, there is a joke by Mark Twain regarding the how we can improve the spelling of English. It's maybe not a joke by Mark Twain, but somebody else. But on the web, it's usually referred to the one by Mark Twain, and it sounds like in his style as well. So you can read this text, but basically it is like very funny how it develops when we just drop some letters gradually, like from year to year. He proposed to drop some letters which are confusing in the spelling of English. And then, like just in the end, I'm reading this sentence, I'm trying to read it, and finally, then after some 20 years of orthographic reform, we would have a logical, coherent spelling in use. This word I can't read. The English-speaking world, or world. So that is like a joke on how the spelling of English sometimes is hard to follow, and that's also like a problem for the models. So models should be aware how we should pronounce correctly the combination of the CH, SH, TH, what is the difference between the J and G, those combinations of double O, EA, double E. So all of this stuff should be learned by the model how to pronounce correctly. And phonemes is one of the ways how we can overcome this problem. And in many papers related to speech synthesis, it is stated that phonemes just help to improve the accuracy a little bit. It's not like a magic thing you can apply and everything will just speak clearly. No, it just like, it's possible to fix some mispronunciations, which is also an achievement. All right, few more topics I wanted to cover in this part. Oh, typo. Okay. First, architecture and like basic Tekkatron we've seen. It is a single speaker model. It has like, it is trained usually like on the corpora, starting like from 10 hours should be enough to train a model, and single voice 10 hours is good enough amount to train a model from scratch and to have like a fair quality of the synthesis, provided that you have a data set of the texts and corresponding audio clips, and it's not dirty, and like many preconditions, you don't have a background music on it or like some disturbing sounds. So it's a clean data set, it is well labeled, and you can train a model. When you want your model being able to speak in multiple voices, then you want to add some information about the speakers. And in my opinion, there are like many ways on how you can add information about the speaker. One of the most straightforward ways is imagine that you have the same Tekkatron model, which is able to take text and produce audio. But now you have like information about two speakers, and you have speaker labels for each of the utterance. And when you have this information, you want to tell model on how to use information about speakers. One of the ways is just to have a speaker embedding layer, which outputs embeddings, let's say in some arbitrary R4064. And that is like an embedding for the single speaker. And let's say that that is somebody like, let's say it's Taras speaking this phrase. And now we want to combine information of the speaker from information from the text with the text information. The easiest way is just to do the broadcast concatenation. So this is like in space of C number of letters, 256. And now we want to do the broadcast concatenation. So we just copy the like letters. And we broadcast the information about the speaker to every letter and the resulting matrix will be number of characters and the dimensionality of 256 plus 464. And that's how we added information about speaker for every letter. It is a prohibited way, but it's totally fine. And it's used widely in many research papers. And it proved working just fine. And now the question is how we are learning these embeddings, how the model should distinguish that is like one speaker from the other speaker. And it's learned in a supervised way. We don't use like any classifications, but we might do those classifications. But the organic way is just to do the back propagation when we are coming back from the loss. We've seen we have the partials or like the gradients of the loss with respect to the speakers. And then having this information, we can update the values of this embedding layer such that our loss will be minimized. So we are updating it to minimize the loss we have. And that way we are just looking for like some places in our like hyperspace for embedding this Terra speaker and some Nazar, let's say. So there are two speakers in our model, and Taras and Nazar like should be now distinguished by the model, provided that we every time we are running like a training, we do this back propagation into the speaker embedding layer. So that is a neat way how we can add information about the speakers. We can also experiment and just since a decoder in the Decathlon is a recurrent module, we can have like it been biased to some value of the speaker Taras or speaker Nazar, and that way we will not be doing this broadcast and concatenate operation. So there are like many ways how we can achieve this. Also, we can take some speaker embeddings from some third-party networks which train to identify speakers. Widely used ways is just to have something from Caldi. That is a framework which I'm not using too much, but it's widely used for speech processing, and it has many recipes on how you can do the pre-neural net stuff, mainly in it, like some Gaussian-based models, GMMs, some HMMs, and many kinds of stuff in it. And also they provide like some ways how you can use the models to get their embeddings on the speakers. So you can use these features which will not be learnable. You just put it like as inputs to the model, and the model will start to make the difference between features corresponding to one speaker and to another. So that is also like many ways to experiment on this. But basically that is like the easiest way how we can make our Decathlon model being functional in multi-speaker scenario. Also, if you want to experiment on the multi-speaker, there is a benchmark dataset which is VCTK. It has more than 100 of English speakers with various accents. So you can play with it and train your Tegatron models. There are like open source implementations on the web. It's an interesting data set to play with. I've trained models with it, it works, so should be fine. Also, one of the ways how we can improve the quality of the Tegatron is to predict multiple representations of the audio. As I mentioned on the first lecture, we have like linear spectrograms, Mel spectrograms, we have gamma tones, we have a lot of features which can be potentially useful for the task of speech synthesis. The one precondition is that we want the nature of those features being as diverse as possible, such that the model will act as an ensemble, and in case they can work complementary, so they can help each other. It's like the different experts in different fields, like one expert which is good at some low frequency analysis, and another expert which is good in some high frequency analysis, and they talk to each other and they can come up with better solution how the model should behave. So the like multiple hats, they are useful, and they are not hard to add to the model. So when everything is done correctly here, the performance shouldn't go down. That is like my assumption. So it shouldn't make worse as the result of the synthesis. It should only make it a bit better. And to conclude this part, we've mentioned that to train the model, we are using an L2 distance, mean square error in the space of the spectrograms. But people usually don't care about the spectrograms. They do care about how pleasant it is to listen to the synthesized voice. Is it interesting to listen to it? Is it intelligible? And that is the most important part. When the model mumbles, it is a model which we don't want to have. We want the model to speak clearly and to convey the information. So for this reason, it was designed like a test on which is named the mean opinion score. It works like this. We have some people, like 100 people, who are asked to listen to the audio samples, the real ones from the ground truth, and synthesized samples, and they need to assign the to assess them using the scale from 1 to 5 on how they like them. So this is purely perceptual metric. It is non-objective at all. And to reflect that this metric is non-objective, take a look at the ground truth MOS score for, it is like 4.58, which is not 5. It means that some people just didn't like how one of the voices sounded, which is absolutely fine. And that's why it's not like, it doesn't have a grade of 5. And what is remarkable is that the like Tegatron 2 paper which is like from the 2018. It has an MOS score of 4.52. It is very close to the ground truth. So it means that in the scenario of the single speaker, the synthesis quality was good even like 2 years ago. But it required for us to have like many hours of the data and many preconditions being been taken in order for training being successful. But in a nutshell, that is like a metric which is reported in most of the scientific papers on the topic of speech synthesis. And also to compare with like the simplest walk order, the Griffin lane, with the synthesized spectrograms, which we listen to, it has a score of like 4, and which is better than the parametric synthesis. So to conclude, it basically means that the majority of the quality of the synthesis comes from the spectrogram's quality, and what the vocoders add is an important part, but it's comparing to the work of the text-to-speech synthesis. I mean, text-to-spectrogram module is much less important because it brings us like additional half of the grade only. So yes, that's it on this part of the lecture. Now I'll open the list of the questions, if there are any, and we'll have a break. Okay, went through the code, didn't have the time yet for playing around with other data sets. It's not a question, just some statement. All right, that's good that you went through the code. I encourage you to play with other data sets if you didn't have time to do this. Next one is, aren't the transaction costs a big issue? When building such portfolios? I'm not sure how should I answer this question. I'm not sure what is the transaction costs here and what is meant by the portfolios. What about the LSTM models? LSTM models, well, the Tegatron model, and it basically incorporates some LSTM modules, so we can get back to the diagram. We have some like conv layers and LSTM layers, so this is like a combination of the convolutional and LSTM modules. There are some purely LSTM-based models for synthesis. I remember there was one from, I guess, Facebook, which was the Melnet. And what they did, they just have like a ton of LSTMs running in time and in frequencies. So to encode the relationships between the time frames and frequency beings across the single time frame. So there are such models, but It is important also to think about the feasibility of this model, since every LSTM model, it requires the information from the past, and we need to wait until we get this information from the past. So it might be very like prohibitive when we have only like LSTMs everywhere, and the time we spend for the synthesis might be very, maybe like a lot of the time to wait for it. So usually we have like some compromise. We want the model to have some sequential nature, because that is what the domain tells us. Our audio itself is sequential, and it's also recurrent. But we also want to compute it in some like manageable amount of time. So that's how it might be. Okay. Looks like we don't have more questions here. Then I'm starting the timer. Let's have a break for 15 minutes and we'll meet some. Okay. See you in 15 minutes. Oh, can you hear me? I was just talking with on the mute for last, I don't know, maybe 3 minutes.
Ross, now we hear you well. All is okay.
Okay. So let me start from the last part of the lectures. It's on the expressive speech synthesis. So as we've seen previously, the MOS are already developed single speaker, multiple speaker TTS models is really high. It's close to the ground truth of the real speech. And but we want to have some ways in how we can control the way our model pronounces text. We didn't have this ability before in plain Tegatron implementations, but we want to have some ways to adjust the intonation, maybe like even I don't know, just to trying to ask maybe the question with the words we are speaking, or pronounce an affirmative sentence, or even give a command is also an important feature for like text-to-speech models. So previously in Tegatron, the plain one, there is no such way to control this. But with the expressive speech synthesis, where we can have a control over the prosody, it is getting more and more feasible. Also, there are like many, like a plethora of the applications of this. For example, we have a well-known speaker like Barack Obama saying his speech to our just the people, and we like the way he speaks it, and we want this way of delivering information being used for some other content. So we want just to take this layer of how he speaks, the way he speaks, and apply it to different text. And that is like an interesting way how algorithms evolve now. Many people are concerned with the deep fakes, and that we are moving really fast into the era of fake content on the web. But I don't think it's a really big problem which we need to be concerned with. And like having these kind of algorithms which speak naturally, it will open us many possibilities. It's like, imagine that you have like a model which is able to convince somebody to don't do some stupid stuff just by using proper intonations, or convince somebody just to grow and evolve. And well, that is a fantastic thing which we can build. And like our communications with the computers and with other people will be changed a lot with the emerging prosodic speech synthesis, the one which is expressive. So what do we mean by the prosody? It is, again, not very well defined concept, but in linguistic, prosody is concerned with those elements of speech that are not individual phonetic segments, but are properties maybe of the whole sentence, or like some like part of the words. So there are some, they have the prosody is spread across many words, and it also tells us like the cultural background of the person speaking. Since people like who are speaking in American English, they sound completely different from those who are speaking in English in Europe, not because the pronunciation is not not the same, since like me, Ukrainian, I'm speaking English with a prominent accent, but the way I speak is also dictated by the cultural background I have, which is different from the cultural background in like other countries. And this background is encoded in the prosody. So it holds the information about the intonations, tone, stresses, and rhythm of speaking. It tells us like much more about the speech and prosody. That's the thing which makes speech convincing. That's more about rhetorics, this ancient Greek study on the eloquence of how to speak. So that is really an impressive part of the synthesis history. So it also reflects the mood of the speaker and also the sarcasm. We can recognize if it's a sarcastic speech by following the intonation, which is like impossible to detect the sarcasm just by looking into the text. It should be like a proper text to see a sarcasm there, but many texts can be spoken in sarcastic way or some other like ways of delivering information. So prosody is everywhere when we speak. So the biggest like problem with the prosody modeling and the one which we face while training these expressive text-to-speech models is that it is really hard to encode it, to disentangle prosody from the words, from the timbre of the speaker, from the acoustic features of the room where the speaker says some content. So we know that prosody is there, but we want to disentangle it such that it will be an independent part which we can just remove as a layer from the content we are delivering. In many cases, the prosody is entangled with the content, but we can for sure understand that there are like some contours of the like pitch which is going up and down, stressing particular words on syllables. And we can take these contours of the varying pitches, for example, and apply it to some other phrase. So that what makes the transfer of the prosody. So we have some monotonous speech and we want to make it more like vibrant. We want to make it more interesting. And we just pick these elements of something interesting from some reference example and we apply it to like some other speech. And coming back to the Tegatron architectures, we've like the basic one is to have a character or phone embeddings, which we've seen before, as well as speaker embeddings as a lookup table, which I also showed on the previous lecture, that we just can do the lookup of the speaker. Then we use the same scheme of like for every character which is in the purple color, we have a speaker embedding which is blue, and we just broadcast it. And also we have some reference phrase which encodes the prosody. And then we are also the same we do with the speakers, we broadcast the prosody across every letter. So the way we can get the relevant prosody on training time is to, we for sure have like the pair of some text and spectrogram. And let's say we have a speaker. So text goes here, speaker goes here, spectrogram now goes to one more encoder, which takes spectrograms, applies some convolutional layers, produces some like summarization of the reference prosody we wanted to have, and outputs an embedding, which we then broadcast. And also the spectrogram, it goes here for the loss computation. So we use spectrogram like in two places now. We use it for like the training of the text-to-speech model, as was before, as a target. And now our spectrogram acts as the source of the features, of the prosodic features, since it's not very clear from where else we can take them. We want to take them just from audio. That is like the best way we can think about it. And like the simplest prosody encoding happens that we just come to the reference encoder with some spectrogram, which is usually like the number of the frequencies, usually it's like 8 ml frequencies, and number of time steps, so it could be t, and we have these kind of spectrogram, and then we reduce this amount to some fixed dimensionality, like that would be like 256. So we can treat this whole process, as lookup of the relevant prosody through like more complicated machinery here than the single layer speaker lookup. And we then concatenate it the same way as we do with the speaker. So that is like, looks like not very complicated way to embed the prosody, but it's important to have it, because on the inference time we can come with the prosody from another spectrogram where we want to take style from. We can use the voice from another speaker, and that is the way how we are gradually starting to have those controls. So now we can control their speaker, We have been able to control text before, and now we are able to control the prosody. And this list goes on and on. So far, we are concerned with how we can control the prosody. And that is like the way the basic implementation. It's also taken from technical group papers on prosody modeling. Or we can also have some labels which tells us if it's like an angry prosody or happy prosody or just neutral. But all of those labels, they hold also like subjectiveness of the opinion. They're not objective. And there is no like gradual. So these labels are hard. That's what I mean. You haven't like labeled it as angry. You don't know how angry this speech is. But the levels of angriness, they are like, it's a spectrum of angriness. There is no such like a single angriness. And that is the way when we don't use hard labels. We don't even use prosody labels here at all. But the aim here is to make the model do its job for trying to disentangle the information of the way of speaking from the text, since here in this prosody embedding, we can also hold all the text information and even spectrogram. That's one of the reasons why the dimensionality size of the embeddings, they're low, and we are trying to like build an information bottleneck. We don't want to have like some phonetical leakage in the prosody embeddings. So we design these reference encoders in the way such that only useful information can travel through this encoder, which is not present in other places. So in case this will be like the same dimensionality as the spectrogram, then the job of the model will be trivial. It could be also like only looking at the prosody, not at text at all, not at the speaker, and it will be doing fine. It will reconstruct the spectrograms, but it will not do something useful. So the requirement for this is to build their information bottleneck. And the simplest information bottleneck is just to reduce the dimensionality of the outputs. So we clearly can see here a compression. In case like T is, for example, like 100 frames, it's already like a compression in several times of the information. And that's what we want to achieve. So these bottlenecks adds like another levels of what our models are able to express. Also for like training the prosodic TTS, it might be interesting also to use like other data sets. the benchmark LJ speech is just like a single voice reading books in some usually like neutral tone. But this neutrality doesn't allow us to really like have a good assessment of the quality of like the prosody transfer or like extraction of the prosody we are doing here. So for this purpose, there is a better data set, which is a part of the Blizzard challenge. And there is a lady, the Catherine Byers, who is reading the some fiction books. It's like 147 hours of audiobooks. And sometimes, or when you listen to those books, it can roar as a like animal. She can roar as an animal, so you can have like huge variety of the emotions and expressions of some excitement or some grief or whatever presented in her voice. So this data set is an excellent candidate for training these models. It is available after the subscription, like just send an email, and in case you're lucky and they approve it, you have a link to download it. So this is like a good benchmark set for validating prosody-like ideas. Also, there is not that many literature available on the prosody modeling. And as I mentioned, it's relatively new study, but there is like one of the researchers who is doing these prosody analysis. He's like Nigel Ward. He have like some papers on the prosody modeling. Also, here is the recorded lecture from last interspeech conference on the like prosody importance, where we should take a look to understand it better. So I will not be playing this lecture now, but it's useful to take a look at it. And again, there is not that many resources on some like academic works on the prosody. At least it is hard for me to find them. So that is like a treasure. He also have some papers on archive, on prosody, and even like books on this topic. So might be interesting for you to explore this a bit more. So yeah, here is like our like more detailed diagram on what we are doing with the like prosody encoding. What I meant like here that we have a reference spectrogram slices, and we basically provide as an input the reference spectrogram, which is here, to the prosody encoder layer. And the same as for the speakers, we just do this broadcast add operation to form like, we have like now 3 encoders to form the whole encoding for this utterance on 3 layers. There is much more things which can be encoded, like an accent of a speaker, but it's hard to get labels on the accents. So languages itself, whatever. So whatever you can find can be used and will give like better levels of controllability, what is synthesized. And in case you're interested in these kind of tasks, just let me know. I'm actively working on this and we are looking for people who want to participate in this research and prosody transfer. So that is what excites me, and that is an interesting topic for the research. Okay. Great. So the basic way to encode the prosody is just to have like a summary, which we don't have like no control on it, right? We have some reference and we have no idea what model extracts there. Is it like a useful information or not useful information? And we want to have like a better degree of control what is happening inside the prosody extraction. For this purpose, there is one more great paper which is based on the style tokens. And the idea of this paper, it also comes from the Decathlon group. The idea of this approach is to like have the same prosody encoder which we had before. So let's take a look at the diagram on the left. So we have an input audio sequence, the same as before. We passed it through the reference encoder and got this vector of the fixed dimensionality. And then we have so-called style token layer, and we design this layer in such a way that we specify the number of the tokens. It's like some atoms, like building blocks of the prosody. Imagine that we have some, that the prosody can be decomposed as a linear combination of some components. And then using this reference encoder and softmax attention, this dot product, the simple one, we are able to find the weighting coefficients for every component of the style, of every token of the style. And this is softmax, and it also means that the sum of these numbers, like 0.2 up to like 0.4, they will sum up to 1. So here we just saying that style token layer, take my reference encoding and give me the individual values for every token you have in order to represent the prosody which I'm taking you as an input. So then after this decomposition happened, we are moving forward in our network with these style embeddings. And these style embeddings now represent a linear combination of some learnable tokens. And these tokens also learned in an unsupervised way, the same way we learn like speaker embeddings. So we also have the gradients of the losses with respect to each of the tokens. And we can backprop into each of those and update them. So this decomposition also gives us like next level of granularity of the prosody. And it doesn't have like some like properties of independent disentanglement. So it means that A and B can be correlated. There is no such a constraint here that they are orthogonal to each other. But we can add those constraints if we want to. But anyway, it's an easy and elegant way on how we can add some controls on it, on the prosody. And it also, this approach, it gives us ability to run inference in a bit different way. So now we can just take those coefficients of each individual style token and just ignore the reference speech. So since we've learned those embeddings, these ABCD, we might not need any more the reference encoder. We have these style tokens, and we want to just specify some numbers on how many of each individual token we want to have in the resultant speech. And it turns out that those tokens, in a supervised way, they are starting to correspond to some particular emotions. And then we have usually, like in case of this model, you don't need like that many tokens. It's enough just to have like 10 of them, such that you can just explore each of those tokens and how it affects the way model sounds. So we can take each individual token and listen to the like synthesis results, having only this one, or just playing with some mixtures, like a bit of token A, a bit of token C, and yep. So that is the way we can leverage this kind of decomposition and add some level, like more granularity on how we control the prosody. So we have the way we did it before. We can predict these weights as we did in the training, or we can specify the weights just manually. And that is like two scenarios which we now have on inference time, which is great. So now we can make our model scream, we can make it cry, or we can do it like sound hilariously or excited. So here, the only limitation we can have is the data set. In case the data set of the speech was really like flat speech with like no, not that much variance in emotions, then those tokens will not hold any like diverse information. Even some of the tokens may hold some information about the room conditions. So it's not like, it is style in a really broad way of speaking. So here style can mean like everything, even the presence of some noise or like some, I don't know, like some missing frequencies in your resultant speech. Everything can be there. And unfortunately, in this approach, there is no way to control this. But anyway, it's elegant on how we can achieve some variation in how our models sound. So just record great data sets from some soap operas and put them into this model, and it will do something interesting in matter of the modeling of the prosody. Okay, let me clear my annotations. Also, I'm attaching here a simple implementation of the style token layer. So layer itself is just a set of the embeddings. We specify 10 tokens, and the embedding size is 520. And that is our predefined, randomly initialized tokens. Not randomly, but with some Javier normalization, Javier uniformly. And on the forward time, what we do here is we take our outputs of the reference encoder, that is a vector of 520 dimensionality, batch and 520, and then we do the matrix multiplication with tokens we have and take a softmax of it. So we have 10 values for each token weight. Also, we can play with temperature here. It's here hard-coded 0.2, but we can supply arbitrary values for it. But on the forward time, we computed the weights for every token, and then we take a linear combination of the tokens given the weights we've predicted from the input data. And now we treat it as a representation of the style, but in the space of the tokens. So again, tokens are learned in unsupervised way. There is no other supervision signals for them. Maybe in case you have some labels, there is possible to give some supervision in order to force some tokens correspond to some particular information you care about. But in case you don't have such information, then the best we can do is just do the unsupervised fitting of these components. So the inference with the softmax temperature is just the same inference process, but we can just play with the temperature. For why we want to play with the temperature, imagine that we have here's token 1, 2, I'll have only 5 tokens. And we have some distribution. Let's imagine that we have a learned model, and we have token 2, which is 0.5, very prominent token, and we have token 4, which is 0.3, and all the rest is distributed somehow, like 0.1 here and 0.1 here. And in case we play with the temperature, we can either push the model into the regime where the distribution will be even. So every token is getting like the same weight. That's not the way I expected it works. So everybody just gets 0.2, or we can get like concentration of the temperature of the weight on a single token. And that is like a neat way, like playing with the temperature and the softmax function to manipulate different temperatures. So we either have like some behavior where like all the tokens are represented, or we just want to explore the single token, but not some particular token, but only the one which gets initial probability the highest. Also, that is like a simple inference when you just specify a vector of the values of the token weights and do the same, just linear combination of the tokens with the weights specified. So that is like two scenarios which we can get in inference time. But again, if in case there is no variety in data, these style tokens will now show something like a miracle. We need to have like proper data sets for model being able to leverage these data and encode these in tokens. Blizzard is great enough for like initial experiments. Okay, so that is like briefly on the how we can represent style. And let's move to other problems. This is an illustration of one of the recent papers, which is published on the last ICML, I guess. And they proposed an elegant idea on how to decompose and disentangle different factors of variation in speech. So they propose an approach which is able to decompose the content. Basically, that is what was written. That is content. Written, it is like the alternation of the speed and pauses, timbre. It's like when we are considering timbre, the easiest way to explain it is that when we have a guitar, it has some specific way it sounds, and the piano. And when we play the same note, the timbre is different, but the note is the same. So the timbre is the way some particular instrument sounds. And pitch is just the translation of like the offset, how high the voice is. So that is like an offset in the scale of the frequencies from like low-pitched voices to high-pitched voices. And here again, everything is about the informational bottlenecks. And also they propose the clever way on how we can add like the way model works and to force disentanglement by random resampling. And their random resampling is an easy procedure. They take, for example, we have like some audio file. It is in a time domain view, and we just pick random slices. So we say that here we want to speed up this part, so it will be pronounced in a shorter period of time. But in this slice, we want to slow it down, and that's also data augmentation, but it's a data augmentation of like simple speed ups and slowdowns in some parts of audio, and that's what they mean by this random resampling operation. And then so imagine that you have like reference speech. This one is unchanged. So we haven't touched the information about the, I guess, about the rhythm, right? So it was like, here it's unchanged, everything's fine. Also, we have, that is like a rhythm encoder. Here, for the content encoder, we applied this operation of random resampling. So we can read this picture like this. This square corresponds to the rhythm, like the solid gray. Vertical lines, it's the content. Horizontal lines, it's should be some pitch, I guess. And this one, their speaker identity, it is corresponded to timbre. So, which is like applies to the same analogy we had with musical instruments. The timbre of me speaking from the timbre of Nazar speaking is different. All right. So by random resampling and basically changing the rhythm information only, but keeping all the rest components untouched, we give it to the content encoder. And the content encoder is not able to encode any information about the rhythm because it's randomly changing. So there is no pattern. It's like just feeding like random information about the rhythm. So that is like the way augmentation acts to force the desired behavior of the module. The information about the speaker comes from here. So presumably, we have a place where we have information about the speaker, so we can also just close our eyes and don't look at the square. And what is like left here? We have content, right, which is unchanged, and we have pitch. Okay, let's remember this. But for its neighbor, for the pitch encoder, we apply random resampling, but not on the audio itself, but on the extracted F0 features. What is F0? F0, it will look like this. It's like so these are just contours of the fundamental frequency, the lowest frequency from where all of the harmonic sounds start to build in some particular voice. And it just shows us the pitch of, like here on the vertical axis, we have pitch, frequencies. Here is time. So here we had like some value of the frequency, let's say it was like 4 kilohertz. And here was a pause, since it's like 0. And you see the picture. It's very simplified, like look at the audio, just a single like fundamental frequency plotted. So we have as input here for this module only this F0 data. So, and this F0, it has by itself information about the pitch and their rhythm. And rhythm is basically these like spaces. So here was the pause, here was the pause, here was that speed, that speed, another speed, and that's it. But information about the rhythm is also randomly resampled. So the only information which this module can take is the information about the pitch itself. So we have an assumption here that in case we can get here only information about the pitch, then it's present in the pitch encoder. So we can ignore it in this encoder and only have information about the content. And also we know that since this information is present, this information is present, and this is present, then the only information which is blocking is the information about the rhythm. And that's why this clever design of all of the information bottlenecks allows us to achieve this disentanglement. Well, idea is clever. I like it, and it involves like only like a single augmentation. But there is like, as usual, like many ways on how we can improve this. The one assumption they make is that the only bottleneck they have is just the size of the output layer. But there are like other approaches on how we can build informational bottlenecks. So that is great. And that was like a research paper from this summer, I guess from MIT and other universities. Idea is neat, and you can look at their demos on the Speech Split website and try to just transfer only pitch information, only content, only rhythm, So that's fun to work on this. Okay, and here is the last part, which is which interests me and, in my opinion, is important for development of the speech synthesis in general. So in many cases, and usually we have the pairs of the text and audio. But there are like many languages which do not have like written forms at all. These are like some tribes somewhere in deserts. They are speaking, they understand each other, but they don't have like ways they write their messages. But we also want to synthesize speech in these kind of languages. Maybe not synthesize, but being able to do like some downstream tasks like the search of the keyword in case you want to understand like find some particular place in recorded speech for some word you care about. You want to have this kind of search being possible. You want to do some image retrieval from speech, like trying to just doing like search of the images, given some speech commands. And what's more exciting, you can even possibly do the speech-to-speech translation. So imagine that you have like some languages which don't have like a corresponding text to them, or like only one language which has English and another language which doesn't have, and you want to understand this person and you want to do the translation with potentially like the synthesis, and that is like something great which can be achieved. And the assumption of these tasks is that when infants, like children, when they learn to speak, first thing they learn is how to speak, then they learn how to write. And they first learn how to speak, then they learn how to write and read. And it is not very clear in which way children are learning how to speak. Presumably, they can build some like proto-phonemes. So we have like phonemes in our languages, like in English, we have like 44 phonemes, which we carefully designed, and we use them as sound units. But presumably children have their own representations of the sounds, which then they can retrieve and build like their speeches based on those protophonemes. But they can do it in a supervised way. They can disentangle somehow the speech they hear. They can rearrange this information and come back with something useful, which then they can use for the synthesis of their own speech. So the goal of this task is to build such models which have limited access to big corpuses. And it also touches like Ukrainian language and many other languages which are which are not widely used in international context, and those languages, they are under danger of being extinct. So these approaches, they can give us like a way in how we can preserve those languages, at least like for the legacy for the future generations. Maybe then we'll change our minds and how on what is important for us, and hopefully this process will be stopped, but we need to preserve this content for the future. As well as we want all of the users of those languages who don't know internationally used languages been able to leverage from the last technical achievements in like, for example, we want to search the documents with the voice commands. And that is more or less doable in English, but it's hard to imagine being working now in some low resource languages. So that is an exciting track of the annual tasks. It started in, as this diagram says, in 2015, and this challenge is the part of the, as far as I know, Interspeech Conference hosts this challenge. So you can participate in this challenge. That is like the way and the place where new ideas are tested, and that is like the place where I believe something exciting in speech synthesis can happen. It also, as I said before, since the task itself is hard for machines to do the synthesis in low resources and without text. So it pushes the boundaries on how we learn the representations, those hidden representations which we got from the like reference encoders, the style tokens stuff, and these disentanglement. They all are fragile, and in case we don't have like some supervision which we get like from when we have like clear pairs of the signal, then we are forced to learn some representations which are robust enough and can be useful for many downstream tasks. So I encourage you to take a look at their website. Unfortunately, the competition for this year is already like finished. But anyway, the data sets are available all year round. And in case you're interested in this kind of research, you're free to play with the available data. The leaderboards are also there, and you can compare with the published results. So Interspeech co-hosts the presentation of the papers in this challenge. So papers usually are published on archive. You can just search for Zero Speech and you'll get many results. So that's basically the finish of my lectures, and I wanted to just share with you what I find like the list of the open questions in TTS modeling, where we can go from here. What I consider is important to solve. So the first important question is, how can we reduce the amount of training data necessary for training TTS models? Yes, we know that TTS models are hungry creatures. They require like tens of hours of data. It is not easy to collect this amount of the training data. And we want to make our models less hungry, just being able and be happy to digest like minutes of data in order to do the proper synthesis in desired voices. That will be fascinating. And this problem is not only relevant to like speech synthesis, this hungriness is relevant to all of the ML algorithms which are connected somehow to neural nets. So that will be a big breakthrough in case we'll be able to reduce the amount of training data necessary for algorithms. Being able to train. Next one is training on data from real life with background noise, low quality audio. So usually in text-to-speech modeling, we look for the clear recordings without some disturbing noises on the background or some like third-party sounds, so like something which makes training harder. We're still looking for something like as clear as possible. And also we have high requirements for the quality of the data. So as I said before, like training in like 8 kilohertz data, like 16 kilohertz is not a best idea. Even 22 kilohertz is questionable. So maybe we need some like super resolution methods which are able to predict the missing information and do the upsampling, which is not possible to do without this information missed. Yes, I guess this is very like important part to come up with the ways how we can be satisfied with the low quality data and being able maybe to improve the quality of the data by the models we learn. So it will open like many good parts, like people with low quality devices, like bad microphones, will be able to record their voices and share them to expand our databases, and then we'll be able to improve the quality of these recordings like programmatically. So it makes a lot of things more possible in this way. Third, effective disentangling of audio data into a set of independent features. That is related to this speech flow approach, to the style tokens and general prosody encoders. We want data being disentangled. We want to have like different layers of content being manipulated on the level of the prosody, on the level of the like speech, voice characteristics. And imagine like having some versatile tool which is able to take some mixed up signal and unmix it. Like Fourier transform do with the frequencies. But we want to bring it to like next level. For sure, we are like care about the frequencies, but we also care about mostly about features we can and desire to change. I'm not sure that like end users or like people want to change like particular frequency. No, they want to have like a control which is more like on the level of abstractions. We are able to think about the audio. And the last one is like learning better universal graphical representation, the text of phonemes. What I mean about this is that it might be that inside neural net we have some like better representation of the some building block units more like connected to text than we have text itself. So as was shown before, text has its own flows. It is like a source of confusion for those who learn languages. It is a source of confusion for neural nets, and might be it's possible to come up with some more like flexible representation, which is not importantly necessarily being interpreted, but might be used and reused in our algorithms. So that is also related to these zero resource languages. When we even don't have these like graphical representations, but might be it's possible just to digest some set of like speech recordings of this low resource language and do some like clustering of nearby sounds and say that these might be like some phonemes or something that resembles phonemes, and they are like combined in this particular way. And in case we have this kind of clustering, which itself like a building of like a language model, then in case it's created, we can resynthesize something new. And it's also interesting how we can bridge the gaps between like different languages with these approaches of some unsupervised encodings and representations of speech units. Yes, so these are like the questions which are interesting to me. Hopefully we'll see the progress in them, and even better if we'll actively contribute to solving these problems. So I encourage you to join the community of those who work with like speech synthesis. It is a lot of fun. It's not a trivial task. It's still unsolved. Like somebody states that computer vision is solved. So that is an interesting place to grow, to learn something new. And thank you for attending this mini set of lectures. Unfortunately, we were not able to meet in person and talk in the classroom. But hopefully next year, the summer school will happen in Lviv. So thank you. Now I'm moving to the questions in case we have those. Oh, this time we don't have questions. Let me recheck. Okay, then thank you all for listening. Wish you great to finish this school and get more knowledge on many aspects of machine learning and data science. Bye.